Jai Hind everyone. This is Nitin Kumar Sharma from Ajay Kumar Garg Engineering College, Department of Applied Sciences and Humanities. And today's lecture is based on the topic ordinary differential equations. This topic comes from the AKGEC second semester Engineering Mathematics 2, for which the code is BAS203. So we are going to discuss. So the content of this topic is definition of the differential equations, order of the differential equations, degree of the differential equations, formation of the differential equations, solution of ordinary differential equation, linear ordinary differential equation with constant coefficient. Complete solution of the ordinary differential equation with constant coefficients. And after all this, we will discuss some examples also. So these are the reference books. You can observe the definition of the differential equation is an equation involving the dependent variable, independent variable, and the differential coefficients of the dependent variable with respect to the independent variables known as the differential equation. For example, we have following differential equations. This is the dy by dx is equal to cot x. So this differential derivative is also a type of the differential equation. This equation is of the second order differential equation. Okay. Then again another type of the differential equation we have here, and this is another type of the differential equation. And see the equation with the radical sign and with the fractional power. So what are the differences between these equations? These equations are the ordinary differential equations, this one also and this one also. But this equation is a special type of the equation based on the type of the differentiation, another type of the differentiation, that is partial differentiation. So this equation is called PDE, partial differential equation. We will discuss it in the next slide. So the ordinary differential equation, a simple definition of this is a differential equation which involve only one independent variable, known as the ordinary differential equation. In simple word, we can say if the equation is containing derivatives of the single independent variable holding function. Like if the function like this, then this will give you dy over dx is equal to f dash x. So this kind of derivative, when this kind of derivatives are involved in the equation, then the equation is known as ordinary differential equation. Next is partial differential equations. As we know that there are two types of the differentiation: ordinary differentiation and partial differentiation. Ordinary differentiation is the differentiation of the type d by dx, and the partial differentiation is del over del x, del over del y type of the derivative. So based on these two type of differentiation, we have the first kind of the equation as ODE, which was these equations. Okay. And this is partial differential equations based on the partial derivatives. So the definition of the equations of this kind is a differential equation which involve more than one independent variables, known as the partial differential equation. For example, we have Px Qy is equal to Z. In another form, we call this equation as, we write this equation as x del z over del x, y del z over del y is equal to z, because these derivatives are also denoted by P and Q. Or simple word you can say, if Z is the function of xy, then del Z over del Z over del x is equal to this, and del Z over del y known as Q. These are the notations for first order partial derivatives. And the second order partial derivatives are del to Z over del x square, del to Z over del y square, and del to Z over del x and del y. So the notations for these are R, small s, and t. These notations are also used in the writing of partial differential equations. So using these notations, we can write another type of notations like if we have x square z xx plus y square z yy is equal to 0. This is another type of the differential equation of partial type. And if we have some equations like r square minus st is equal to 0, this is another differential equation. Okay, these are the second order partial differential equations. So what we have here, the first thing, that is order of the differential equation. How we can determine the order of a differential equation? And here we are basically concerned with the ordinary differential equation. So order of a differential equation is the order of the highest ordered derivative available in the differential equation. Like for example, we have in this equation, if we observe, the highest order derivative is with first order, and here it is also the derivative with the first order. So the order of this equation is equal to 1. Okay, then the order for this equation, we can see here it is the first order derivative. And here it is second order derivative. Then the order of this equation is 2. Okay, now if we consider this equation, then the highest order derivative in this equation is d2y over dx square. So the order of this equation is also 2. But we will discuss this equation once again in the case of the degree. So I would like to write some equation here like d square minus 4d plus 1 y is equal to suppose x sin x is here. So this is another type of the notation for the ordinary differential equation, and the order is decided with this power of d, where this d stand for d over dx, opted del over del x. Let me write it once again. Okay, so the next is, all right, now we will discuss the degree of the differential equation. First of all, the definition of the degree of differential equation. Degree of a differential equation is the power of the highest order derivative available in the differential equation when it is free from radical signs and fractional powers. So you can see here, if we consider this equation first, then the highest order of this equation is occurring here. Derivative of higher order is occurring here. Therefore, the order of this equation is 2, and the power of this derivative is 1. So the degree of this is 1. In similar way, if we consider this equation, and first of all we have to simplify this like this, del d2y over dx square and rho, and then take the square because here it is a fractional power. So take the square on both sides is equal to, we have 1 plus dy over dx whole square and then power 3. So now we can decide the degree, because if we take this part to the left hand side, then it will become 0. So now the order and degree can be easily decided. So the order of this equation is equal to, given by the highest order derivative, which is given here, that is 2, and the degree given by the power of this derivative, and the power of the derivative is 2. Therefore, it is 2. So order and degree are now defined. Okay. Then next is a differential equation of the linear differential equation with constant coefficient type. So here we are going to consider the linear differential equation of the constant coefficient type. So a differential equation of the form a naught d raised to power n y over dxn and a1 dn minus 1 y dx raised to power n minus 1 plus a2 d n minus 2 y over d x raised to power n minus 2 plus and so on, plus here it is a n y is equal to any function rx, right? Okay, then this kind of equation known as the ordinary differential equations with constant coefficient, where the a naught, a1, a2 and so on, an are constant coefficients and Rx is any function of x only. So why it is x only? Because here we are considering the ordinary differential equations. So in the case of the ordinary differential equation, we have the functions of single independent variable only. Therefore, here it is the function of x only. Okay. Now, to study in detail this kind of equation, we have to, whenever we are going to solve these kind of equations, so we have to convert this form using the notation d over dx as operator d. Then it is converted into a naught d raised to power n, a1 d raised to power n minus 1, a2 d raised to power n minus 2 and so on, plus any is equal to rx. So after that we will take the y common from all these, then this is a polynomial in D. So we can write this polynomial as fd y, and on the right hand side we have rx. So we have a very shortest form, we can say shortest form of the ordinary differential equation with constant coefficient, where fd represent a polynomial in D with constant coefficient a naught, a1, a2, a3, an. Okay. So next is Next is the solution of the differential equation. The solution of the differential equation with constant coefficient. So first of all, we have to understand that what is a solution. The solution for a differential equation is an expression which can satisfy the given equation. So here we have some theory that a solution of a differential equation is a relation free from derivatives between dependent and independent variables which satisfies the given ordinary differential equation. Like if we write an example, suppose we have d2y over dx square minus y is equal to 0. Then the solution of this will be y is equal to, if we solve this equation, then we will get plus minus 1, and the solution will be c1 e raised to power x plus c2 e raised to power minus x. Okay, then this expression, if we substitute this expression in the LHS of this equation, then the result will be 0. So this will satisfy the given equation, and this is why we call it the solution of this given equation. That is the solution of this equation. Okay, then next thing is the complete solution. There are types of the solutions. Out of that, we have here complete solution, we have here complete solution, general solution, and particular solutions. So complete solution, in the case of the ODE with constant coefficient, the complete solution means a solution which has y is equal to CF plus PI, because the solution of this equation has two parts, CF and PI. Then what is CF? CF is the complementary function and PI is particular integral. Now here we have to understand that which part is determined from which part of the given equation. So the LHS of the given ODE of f dy is equal to Rx. If this is the given ODE, then the LHS is liable for the CF and the RHS is liable for PI. That means if we have an equation, if an equation is given to us, if f dy is equal to 0 is the given equation, then we have only CF here. Then the complete solution given by y is equal to CF plus 0. And why this 0 is here? Because Rx is 0 here. So the PI will be 0. The PI will be 0. This is why here we have to write y is equal to CF plus PI. Okay. Then one more thing here. Okay. Then if we have the equation with Rx and Rx is non-zero and Rx is not equal to 0, then here we have to determine the PI, and this PI will be non-zero in this case. PI will be not equal to 0 in this case. Okay, so let us move forward. Now, the general solution. What is the general solution? General solution is the solution if the number of arbitrary constants is equal to the order of the ODE. If number of arbitrary constants is equal to the order of ODE, then what is the arbitrary constants? And order we have already discussed. So let us take an example here. Once again, we can write here an equation d2y over dx square minus 4y is equal to, suppose we have sin x. Okay. Then, in this case, let us take RHS 0 because we have not to extend this example length. So we have the example like d2y over dx square minus 4y is equal to 0. Suppose this is the equation. If we again erase this part to write it very clearly, dy dx square. There is a problem in the pen sometimes. Dx square. Now this is the example for the general solution, that the solution of this is given by c1 e raised to power 2x plus c2 e raised to power minus 2x. This is the solution of this equation because RHS is equal to 0, that is Rx is equal to 0, so Pi is equal to 0. So here we have the complete solution as Cf is this and Pi is equal to 0. So now what is the arbitrary constant? So here C1 and C2 are arbitrary constants. C1 and C2 are arbitrary constants. These are the arbitrary constants. Okay, and now you can observe that the order of this equation is 2 and the number of arbitrary constant is 2. So this solution is ordinary, this solution is general solution of the given ordinary differential equation with constant coefficient. Okay, next is the particular solution. If we assign some particular values to the arbitrary constant in general solution, then we get the particular solution. Like the given solution above is y is equal to c1 e raised to power 2x plus c2 e raised to power minus 2x. So in this case we have two arbitrary constants. So if c1 is equal to 1 and c2 is equal to, suppose, minus 2. For instance, we are taking these values because these values are determined with the given conditions. So for instance, we are taking that c1 is equal to 1 and c2 is equal to minus 2. So if we put this in this equation and in this solution, then in place of c1 we are writing 1. See, it is 1 into e raised to power 2x plus minus 2 e raised to power minus 2x. So this will become the particular solution. Here you can say that this was the general solution and this is particular one for the same equation. Okay. Now the next slide is complementary function. Now how to write the complementary function? During this slide, many of you was thinking that how we can determine the CF and PI to write the complete solution. So now we are going to understand how to write these CF and PI. So the complementary function. In this lecture, we will discuss the complementary function only, and in the next lecture, we will discuss the PI, how to write the PI. So this lecture is dedicated specially for the complementary function. Okay, so these are the working steps. Then first of all, write the given ODE such that f dy is equal to Rx. Why I am saying that? Because in the last slide you can see that usually equations are given to you in this format. So you have to convert the given equation in the format like this. That is, for example, you have to take all d by dx like capital D. Then you will get the polynomial. Okay, we will discuss it in the next example. Okay, then second, now create auxiliary equation. Create auxiliary equation by taking d is equal to m and y is equal to 1 in LHS, especially in LHS. Such that f m is equal to 0. Then in the third, solve fm is equal to 0, that is your auxiliary equation, for roots and decide nature of roots. Then in the fourth step onward, you have to write, now write CF as per roots of AE. Okay, so these are the simple working steps. Then when roots are real, if the nature of the roots are real, like, but here another case is that in each and every type of the case you have two types of the roots, repeated and distinct. So first of all we are writing when roots are real and distinct, that is m1 is not equal to m2 is not equal to m3. Then in this case the CF is given by the C1 e raised to power m1x, C2 e raised to power m2x, and C3 e raised to power m3x. Okay, and so on if we have further roots. But in the case of the repeated roots, real and repeated root. So if we have, suppose m1 is equal to m2 is equal to m3, three roots are same, and suppose the common value is m, then we have to write it like CF is equal to C1 x C2 and x square C3 and e raised to power mx. If we have only two roots repeated, suppose the third is not equal and both of these are same, so in this case we have to write C1 plus x C2 e raised to power mx if this root is common, and plus the third root is written like c3 e raised to power m3x. This will be the CF for this case. Okay. So now the example for the real kind of the roots. Suppose this is your equation where d cube minus 3d square plus 4 is the FD and y is here and is equal to 0 means Rx is 0. So if Rx is 0, then here we can see the Pi is 0 because Rx is 0. Okay. Then form the auxiliary equation, and the auxiliary equation is formed by substituting d is equal to m. So if we substitute d is equal to m, we have m cube minus 3m square plus 4. Now solve this equation for the roots and we got the root like this. And here you can see this is the case of this kind of CF where 2 and 2 are repeating and minus 1 is distinct from these roots. So out of these last two roots are repeating, so we have written c2 plus c3x with e raised to power 2x and c1 as the distinct root c1 e raised to power minus x. So Pi is equal to 0. Therefore, the complete and the general solution of the given equation is y is equal to Cf plus Pi and is equal to c1 e raised to power minus x plus c2 plus c3 e raised c3 c3 x and e raised to power 2x and plus 0. So this is the complete solution of this equation. Complete when the roots are imaginary. So when roots are imaginary, then we will get the roots of the auxiliary equation like alpha plus minus I beta. These roots are the imaginary roots and never exist in the single. So therefore, the root exists in the pairs. So here we have two roots and both the roots are distinct. So in this case, we will discuss m1 as alpha plus I beta and m2 is equal to alpha minus I beta. Okay, then the manner to write it is CF is equal to e raised to power alpha x because both of these roots are distinct. So here it is the case of the distinct roots, imaginary and distinct. I am writing right here again, imaginary and distinct root. Okay, so e raised to power alpha x c1 cos beta x c2 sin beta x. Okay, but in the case of the imaginary and repeated roots, so m1 will be equal to the m2. In this case, m1 will be equal to m2. That is, here we have to take 4 roots in the case of the complex functions. So here we have m as alpha plus minus I beta and alpha plus minus I beta. Okay, so m1 will be equal to m2. So these, in the case of the positive, we have the m1 and m2 and then m3 and m4. Okay, so in this case we have to write the CF as, let me write it in detail. So if we take the positive roots, suppose m1 here is equal to alpha plus I beta and is m3 is equal to alpha minus I beta. So the m2 is also and m4 is also the same after writing these two roots separately, these four roots separately. So we have e raised to power alpha x, which is the common real part of these roots. Okay, then for the repeatance of the root, c1 x c2 and cos beta x plus c3 x c4 sin beta x. This is the manner to write the repeated roots in case of the imaginary and repeated roots. Okay, now this is the example. Here you are given with the equation of the ODE type with constant coefficient. Then the auxiliary equation, if you replace this as, we can write this equation as d raised to power 4 minus plus 13d square plus 36 and y is equal to 0. Then this is fd, and substitute d is equal to m and y is equal to 1. So we will get the auxiliary equation like this. Okay, and then after solving, we got the root. Here you can see, and two pairs of the root, and all are the imaginary and distinct. So here the nature of the root is imaginary and distinct. Why you can say distinct? Because here it is 0 plus minus 3i and iota and 0 plus minus 2 iota. Okay, so here we have four roots and all roots are distinct. So if we write it separately, so m1 is equal to plus 3i, m2 is equal to minus 3i, and m3 is equal to plus 2i, and m4 is equal to minus 2i. Now for these four roots, we have to write the CF, and the CF here given by, because the real part of these two roots, these two pairs is 0, then e raised to power 0x and c1 cos 3x plus c2 sin 3x is for the first pair, and e raised to power 0x c3 cos 2x plus c4 sin 2x for the second pair. Okay, or we can write it like this, but the general solution, because Rx is equal to 0, so the Pi is equal to 0. Therefore, general solution is y is equal to Cf plus 0. Why is 0? Because Pi is 0. And just write the Cf here will be the complete solution of it. Okay. Here it is the given ODE, and the auxiliary equation is m square minus 2m plus 4 whole square. And then you can see after solving, we got these roots. Here you can see the roots are repeating. That is, the first pair is same as the second pair. So in this case, we have, if we write m1 is equal to 1 plus root 3 iota, and m2 is equal to 1 minus root 3 iota. Then you can see it is m3 also the same and m4 also the same. Therefore, in this case, the CF is given by, the real part. First of all, the real part, e raised to power 1x, and in the bracket c1 plus x c2 cos root let us erase it, c1 root 3x plus c3 plus x C4 sine root 3x. This will be the CF, and because the Rx is not available here, so the Pi is equal to 0. Therefore, the complete solution is y is equal to CF plus Pi, and is y is equal to the given CF, that is CF plus 0. So if we write this CF here in this equation, then we will get the complete and general solution. Why we are calling it a general solution? This solution is the general also, because the number of arbitrary constants C1, C2, C3, C4, we have 4 arbitrary constants here, and the order of this equation is 4. Why? Because the highest power in this polynomial is d square, and after squaring this you will get the polynomial with the power 4. Maximum power will be 4. The order of the differential equation is 4. This is why we have used here arbitrary constant 4, arbitrary constant. So the solution is the general solution here. Okay, so the next slide is when roots are irrational. Similar to the complex imaginary roots, we have when roots are irrational, then there are again 2 cases. Irrational roots are like this, plus minus root beta. These are the type of the irrational roots. If we have distinct root, if we have irrational and distinct roots, irrational and distinct, then suppose alpha plus minus I beta. If you, sorry, I is not here, suppose it is 1. If you write it separately, then you will get m1 is equal to alpha plus beta root beta. You can see right here, root beta, and m2 is equal to alpha minus root beta. Both of these are the irrational roots. So in this case, we have to write the CF as e raised to power alpha x and C1. Here we have to use hyperbolic cos, and root beta x plus C2 sine hyperbolic sine root beta x. This is the way to write the when roots are the irrational roots and distinct roots. When roots are irrational as well as repeated, I am writing this is as repeated. So if roots are repeated, then we have m as alpha plus minus I beta, alpha plus minus root beta, and again another pair as alpha plus minus root beta. So in this case, the CF is given by e raised to power alpha x in the bracket C1 x C2 hyperbolic cos root beta x plus C3 x C4 and hyperbolic sine and root beta x. This is the way to write the complementary function in the case of the irrational roots, distinct and repeated. So now the next is particular integral. We will discuss this topic in the next lecture. Okay, so this was a lecture for today, and we will discuss some more examples with the complementary function and the PI in the next lecture. So till then,